Okay, so step two, 2019, question 10. Now, yeah, I definitely like this question, to be honest with you, and I was quite surprised I like this question because I've always had this kind of I suppose, nervousness about mechanics questions, but the more I do them, the more I really like them, and the more I think that actually this is more straightforward. Once you have the diagram correct, this is more straightforward than the pure questions. Now, I did not get this diagram correct when I first drew it. I probably had about 2 or 3 false starts where I reread the question, looked at my diagram, thought that doesn't make sense, etc., etc., etc. Eventually, I read the word horizontal and realized that the rail is here and it's flat because it's horizontal. Now the bar, or the rod, sorry, AB makes an angle theta, and it only makes sense for that to be below the rail as the string is actually holding it up and keeping it in equilibrium. Now it's important to note that this is actually going to be an isosceles triangle as well, because that's of length 2a, the bar AB, and it's uniform, so the weight is in the middle, and the string is of length 2a as well, and hence it will form an isosceles triangle. That's really, really useful to realize. You're not going to get anywhere without that. I also chopped up, so yeah, that's the rail, and this is the rod, and this is the string just here. So hopefully that clears up what's going on here. The other thing which was really tricky for me as well, it's not actually that tricky, but you realise you want to resolve T perpendicular to the rod, because what I'm going to do to try and answer this question is take moments at A, and that's because I really want to get rid of the two forces provided by the ring slipping on the rail, which is R and F max, which is of course mu R. So the rod wants to slip in that direction, you see, because obviously it's getting pulled across by the weight and the tension. Well, it's the tension actually pulling it to the right, and so the friction's going to be operating to the left. And so I want to take moments at A to knock out, if you like, the R and the F max, and then that should give me a nice little equation which I can use. Now, what I'm going to do is I'm going to assume that everything is in equilibrium. Yeah, so I'm going to assume that the string hasn't broke yet. Let's assume that it's in equilibrium. Now, if it's in equilibrium and we take moments at A, we're going to have A times W cos theta plus, okay, distance times by perpendicular component of force. That'll be 2A times W, KW, sorry, WK if you like, cos theta. So those are the moments which are turning the rod in that direction, and they should equal the moments turning the rod in the other direction, and there's only one force which is turning that rod in the other direction, and that is this T force here, but I need to resolve it perpendicular, so that's going to be T cos multiplied by 2 theta minus 90. Yeah, and like I always say with any mechanics question, you want to get, oh, and I forgot the A, I forgot to times by 2A, sorry. But just like any moments question, you want to get that initial equation absolutely spot on and correct. So do check it after you've done it. Now, just like any other moments question as well, the A's cancel. And so let's factorize out the W cos theta there. And we're going to get a lovely 2k plus 1, I believe. On the right hand side, I'm going to write the 2t, but then I'm going to do a compound angle essentially on this. I'm going to say that's the same as cos 2 theta cos 90 plus sine 2 theta sine 90. Oh, I'm going to the edge of my screen. I'm going to move over a little bit just so I can squeeze that 0 in on the 90. Okay, and now I'm just going to simplify everything. So I get W cos theta multiplied by, oh, that's so annoying, I keep missing out the argument on my trig angles, I apologize. So I get W cos theta multiplied by 1 plus 2k equals 2t, and now if you look, this tidies up quite nicely because cos 90 is 0, sine of 90 is 1, so you're left with sine 2 theta. But everybody knows that sine 2 theta is the same as 2 sine theta cos theta. Okay, next step, I'm going to divide through by cos theta, Now, can I do that? Always be careful, you might be dividing by 0. Well, it did say that theta was definitely less than 90, I believe, in the question. It said theta was between 0 and 90, I believe. Yeah. And so we can safely divide by cos theta because cos theta can't equal 0 if theta isn't 90. If it's trapped between 0 and 90, cos theta is trapped between 0 and 1. So, yeah, or, but strictly greater than 0. So we can divide by cos theta. And then we're going to end up with 4 times 1 plus 2k equals 4t sine theta. Now let's not assume equilibrium. Now let's actually get back to the question, because the question said you are given that the string will break if the tension is greater than W. Show that, assuming the ring does not slip. Now there's where I've assumed the ring does not slip. Assume ring doesn't slip. So I've assumed the ring doesn't slip by assuming equilibrium. That's how I've taken care of that assumption. Well, now what I'm going to do is I'm going to assume the string breaks. I.e. T is greater than W. And if T is greater than W, well, T is clearly, if the ring does not slip, W times 1 plus 2k over 4 sine theta. Yeah, that comes just from a rearrangement from here, that T is W plus times 1 plus 2k over 4 sine theta. So that's all I'm using there. And that's got to be bigger than W. The W's cancel either side because the weight is strictly greater than 0. Once again, I can do that. And I end up with their answer that 1 plus 2k is bigger than 4 sine theta. And that is part A done, or part 1 done. Okay, hope that makes sense. Now, part B, I'm going to use a really kind of similar approach, to be honest. It's going to involve a little bit more work, but essentially it's going to be exactly the same kind of idea. This time, though, I'm going to need to do moments at B, and that's because I'm going to not assume that the ring doesn't slip this time. I'm going to find the conditions for which the ring slips if the string doesn't break. And it's moments at B which will help me to achieve that. So, okay. Sorry, just rubbing out my working here. I hope that makes sense. Okay, so let's try moments at B this time. If I do moments at B, I now knock out the T and the KW, which is kind of nice. And I'm going to have AW cos theta again. Plus, if you look, that mu r, let's do this in red like I've done all the other perpendicular and parallel bits. Well, if that's theta, that's 90, so that's 90 minus theta. So this bit here is theta. And likewise for this r, that's parallel, that's perpendicular. That's theta. You'd have 90 minus theta there, theta up there. And so we're going to have 90 minus theta here, and therefore theta up here. Sorry about my terrible handwriting there. It's tricky on the graphics tablet, but I hope it makes sense where you can see those thetas go. Should be relatively straightforward drawing those little right-angled triangles and getting the theta in the right place. So anyway, this mu r is actually going to be mu r sine theta if I resolve it perpendicular to the rod. So I'm going to have 2a mu r sine theta. And then that is going to be equal to r sine theta, 2a r sine theta there. Oh, sorry, 2a r cos theta. And that's because I want this side of that little right-angled triangle. And that's cos. So I'm going to have 2a r cos theta for that moment there. Okay, so that's moments at B. Now, what have I really done here? I've said, okay, let's assume it's in equilibrium, which is another way of saying this time I'm assuming that the string doesn't break. And I'm going to find out, well, I'm going to simplify this, and obviously the a's cancel again, and then using this and perhaps ups equals downs principle and lefts equal rights principle, I'm going to use those three principles to try and come up with their inequality. At the end, of course, I'm actually going to assume that the ring is slipping, which means that this equation will turn into an inequality. But let's just simplify it first, and we're going to get w cos theta plus 2 mu r sine theta equals 2r cos theta. Now, for my lefts and rights here, and this is the way I always do it with my classes anyway, lefts equal rights, ups equal downs. What I'm going to do is I'm just going to say, okay, looking at that, there's only really mu r going to the left and t sine 90 minus theta going to the right. Now, sine of 90 minus theta is simply cos theta, and cos of 90 minus theta is simply sine theta, and you want to be aware of those identities very quickly in your head. So this is just t cos theta, actually. So that's what I get for my lefts equal rights. And my ups equal downs. Well, what am I going to get for that? That's a little bit more, that's a bit more to it. You've got r plus t cos 90 minus theta. And yes, that is just t sine theta. But r plus t cos 90 minus theta equals w plus kw, which is w times 1 plus k. And therefore, I've got r plus t sine theta equals w times 1 plus k. Cool. So here I've just assumed that everything is in equilibrium, and those are the equations that I get. Now remember as well, really, because I've used mu r, which is F max, I am really saying it's in limiting equilibrium, and so it's on the point of catastrophe, if you like. The system is on the point of changing. It's about to go from static to dynamic. It is the limit of the equilibrium. Now what I'm going to do is I'm going to change that, but first, let me just use a couple of useful facts from the limiting equilibrium scenario. We can now say that t equals mu r over cos theta. And I can also say that w is, if I just quickly rearrange that, what am I going to get? R plus t sine theta over 1 plus k. But let's even go further, actually, and let's plug this into here so we get rid of the t's. We don't want any t's in our working, so we need to get rid of that. So we're going to get r plus tan theta mu r. And I'll put that in brackets so it doesn't look like I'm taking a trigger, applying tan to it. And so let's just quickly simplify that. What do we end up with? We end up with w equals r times 1 plus mu tan theta over 1 plus k. Okay, but we're supposed to say, if you look in part 2, we're showing that assuming the string doesn't break, the ring will slip. So the ring will start slipping, actually, if our original moments equation is not an inequality. It's not an equality, but in fact is an inequality. In other words, if the moments which work to the left suddenly are less than the moments, I should specify the direction, I apologize. If we suddenly now have, for the moments at B, if we suddenly turn that into w cos theta plus 2 mu r sine theta, well, if that was actually less than the turning force to the right, which is 2r cos theta, then the ring starts slipping. So what I'm going to do now is I'm going to substitute in w, so it's in terms of r, and I end up with r 1 plus mu tan theta over 1 plus k multiplied by cos theta plus 2 mu r sine theta is less than 2r cos theta. Now the nice satisfying thing about that is my r's disappear now and I'm left with an equation just involving mu and theta and k, which is what I was looking for. So let's cross those r's out. And that's good. And let's also now rearrange this essentially into what we're looking for. I'm going to multiply everything by 1 plus k. I can do that as k is strictly positive, so I haven't got to worry about the inequality. 1 plus mu tan theta cos theta plus 2 mu sine theta 1 plus k is less than 2 cos theta times 1 plus k. Always look a bit where you're going here. What I'm now going to do is I'm going to multiply out these. I get cos theta 1 plus cos theta plus mu. Now tan theta times by cos theta is of course sine theta plus 2 mu sine theta plus 2k mu sine theta, and that's going to be less than 2 cos theta plus 2k cos theta. Let's simplify it. Let's collect the cos thetas together. That's going to be giving me just a cos theta on the right hand side. And I've got a 1 and I've got a 2k cos theta as well, so I could just write it as 1 plus 2k. That seems sensible. And then on this side, I've got 3 mu sine theta. Oh, plus 2k mu sine theta. So I'd make that, if I take out the mu sine theta, I think I can make that 3 plus 2k. And then I think I'm very close to the answer now. Let me just, I'm sorry, I'm constantly referring to the question, which I've got written down somewhere nearby. So that's 2k plus 3 mu tan theta. I've basically got the answer now, haven't I? I can safely divide by cos theta because it's strictly positive from 0 to 90. And so I get mu tan theta 3 plus 2k is less than 2k plus 1, which is essentially what they've got just written down the other way round. So that's as required. And you're done. And if you want to have a little look at what you've actually achieved there, we assumed that everything was in at the point of slipping, just about to slip, that the string was just about to break, if you like, and made the lefts equal the rights, the ups equal the downs, and the moments equal each other. But then we said, okay, well, let's say the ring slips. Let's use the moment at B equation and point out that the moments to the left are less than the moments to the right, and then we've got our final answer. Okay, hope that makes sense. Let's now go on to part 3. It's just going to take me a little while to rub everything out. Apologies. Part 3 is really, as you would expect often in step questions, it's all about using part 1 and part 2 to derive part 3. And actually, the good news is I haven't got to take moments anymore. And this is the thing about the applied questions in step. They feel really like the applied aspect of it is just a bit of varnish, or sorry, veneer is the word I'm looking for. It's a facade, really. Really, it's pure maths. It's just trig. There's lots of trig going on there. But the applied step is just in the very first step. And if you get that step right, the subsequent pure maths that you'll do will be easier than the pure mathematics in a typical pure question. So if you can just get the diagram right and set up the initial moment equation right, you're good. And part 3 is no exception. Yeah. So in part 3, it's saying, okay, if we increase k gradually from 0, we're told that we're given. Let's write down what we're given first because it might come in handy. It always does, to be honest. In fact, if you don't use something that they gave you, you've probably done the question wrong. So we're told that. So let's see if that comes in handy at some point. And now we're going to increase k gradually from 0, and we're going to hope that the ring will slip before the string breaks. And we're going to prove this condition if those two hold this condition involving mu and theta. So, okay, what have we got here? Well, we already know. Let's write down what we know, but I'm going to do it slightly differently. I'm going to say, okay, if the ring slips, if the string breaks, and that's assuming ring doesn't slip, then we know that 2k plus 1 is greater than 4 sine theta. Yeah. So let's just say if string doesn't break, that inequality is going to work the other way around. 2k plus 1 is going to be less than 4 sine theta. Yeah, if the string doesn't break. Okay, right. And then from part 2, we worked out that, like, the ring slips if 2k plus 1 is less than 2k plus 3 mu tan theta. And so in part 3, what do we want? We want the string not to break and the ring to slip. So we want those two inequalities to hold. Yeah, we don't want the string breaking, but we also want the ring slipping. So we want these two inequalities to hold. What I'm going to do is I'm just going to work out the conditions on K for both of these to be true. Now the first one, if we give this a different name, actually, let's call this one like smiley face or something like that. That's often what I use. Okay, smiley face. If we call that one smiley face, well, from smiley face, we can see that K is definitely going to be less than 4 sine theta minus 1 over 2. Yeah, and it's okay to divide by 2 there. It's greater than 0. I haven't got to worry about what it does to the inequality. Similarly, from the star, I can see that, now this is going to take a little bit more work to get this in terms of solely K. If you rearrange it, you can get 2K minus 2K mu tan theta is going to be less than 3 mu tan theta. And let's just rearrange that so it's in terms of K. We'll have K as SM 3 mu tan theta over oh, hang on, have I made it? Oh, I've forgotten about the minus 1. Yeah, I need to take away that 1 there. Sorry about that. I just totally didn't spot that. 2k minus, yeah, because I've moved it over without, yeah. Okay, divided by 1 minus mu tan theta times 2. Hope you're happy with that. And that should be all good. Have I written down this inequality the right way from part 2? I feel like I have not written down, look at that, I've actually written down the inequality the wrong way. It's so easy to make careless slips in your algebra. I do it all the time, I really do. So let's just turn those all back to front. And then we've got, that's the right way round now, that's the right way round now, and that's the right way round now. So we've got two conditions on K. Now, that's great, because if you look at it, K is now sandwiched. That's the next thing I notice. K is sandwiched. It's less than this value here, but it's definitely bigger than that value there. But it doesn't take too much imagination to think, well, that means that 4 sine theta minus 1 over 2, that must be the biggest one, and that must be bigger than 3 mu tan theta minus 1 over 2 minus 2 mu tan theta. Well, let's just cancel the 2's, actually. That would be the easiest way, wouldn't it? Cancel the 2's. And now, here's where you use the fact that mu tan theta is less than 1. If mu tan theta is less than 1, then this here is strictly positive. And we need that to make sure that when we times it across the inequality, we don't have to, switch the direction of the inequality. That's why they told us that. We needed that. We really did. And the fact that I'm using that in this step told me, I'm probably doing this right. So you're going to times that bracket by this in brackets, if you like. And so you're going to get 4 sine theta minus 4 mu sine theta tan theta minus 1 plus mu tan theta, and that is going to be bigger than 3 mu tan theta minus 1. And let's just keep going. We're almost at the end now. Let's just tidy up a bit. Tidy up, tidy up. Okay, I've got a 3 mu tan theta and a mu tan theta there. I've got two minus ones. Let's get rid of those. That's going to be 2 mu tan theta. Over here, we've got 4 sine theta minus 4 mu sine theta. I think I might take out the 4 sine theta actually here. And then that gives me 1 minus mu tan theta. Sorry about my wonky handwriting here. Now, if you think about it, there is a sine theta in there, isn't there? Because tan is sine theta over cos theta. So I can safely divide by sine theta throughout. And once again, I don't have to worry about it being negative because between 0 and 90, sine theta is strictly positive. So that's going to give me, oh, I can also divide by a factor of 2 here, change that into a 2 and change that into a 1. And so I'm going to get 2 times by 1 minus mu tan theta. Well, that's bigger than, what have I got here? Mu tan theta. Now, I want to make mu the subject of this, don't I? So let's do 2 and then is greater than mu, and then it's going to be tan theta, 2 tan theta. Oh, right, hang on, that's just 3 mu tan theta, isn't it? And I've made a mistake somewhere. Where have I made my mistake? I do this so often, honestly. Let's just go back here. I'm pretty sure it was right there. I divided everything by sine. There should be a cos still involved here. Sine theta, tan theta. Oh yeah, that's just going to become over cos theta then, isn't it? So let's get that right. When I divide through by sine here, I'm left with mu over cos theta. That's better. Is going to be 2 minus 2 mu tan theta. When you go wrong like that, it's almost invariably because you try to skip too many steps like I just did. That's going to give us, let's times by cos theta now, 2 cos theta minus 2 mu sine theta is greater than mu. Put the mu over there, 2 cos theta is greater than mu times 1 plus 2 sine theta. And lo and behold, I think we've got it now. I'll have to check, but it looks to me like this is going to work out as mu is less than 2 cos theta over 1 plus 2 sine theta. Apologies that my handwriting's got so poor at the end there. But yeah, that is the question. And you've finished and it's done. Whew, not too bad, eh? I thought that one was not too bad at all.